Okay, thank you for coming tonight. And this is a talk, as I was just saying, that I've been wanting to organize a bit. Ultimately, this will be a chapter of a yet unwritten book, but it was a good opportunity to get a few things together here about George Comstock, who was the third director of Washburn Observatory, and very important to the history of Washburn Observatory, if for no other reason that he was the director for over 30 years, and so left an important stamp, 35 years, I suppose, left an important stamp on the department, but is interesting in a number of ways in the way that he fits into the history of astronomy and in the work that he did in and of itself. So it's often described as sort of positional astronomy, but you'll see that what I want to set up here really is that Comstock's work in those years was laying foundations of modern astrophysics and stellar studies in a number of important ways. So Comstock himself is actually a Madison native, although he did not grow up here. When he was still young, his family moved out of Madison, and he grew up in Kenosha and then in a few towns in Ohio, where apparently his father was traveling for business, but was a talented enough youth that people were looking for ways to get higher education in a time when, of course, families had to pay for that in any number of ways. And his idea was to get admitted to the Naval Observatory at Annapolis. And there was, at least in Ohio, the way they did that was there was an exam, and you could take the exam, and if you ranked highly enough, then you could get nominated to go to Annapolis. And the young Comstock, who was mathematically quite talented, scored first in the state on this exam, and so had admission to Annapolis, except that apparently his mother talked him out of it. She had active memories of the Civil War in those days, and she did not want her son to go to a military career, and so apparently they compromised. She agreed that they would move to Ann Arbor and help support him while he went to college at the University of Michigan. So as an alternative to Annapolis, he might have ended up at the Naval Observatory or something, who knows, but in fact he ended up at the University of Michigan in Ann Arbor, where he was partly supported by his family and partly supported by his own efforts. He worked a number of summers and gained a lot of skill as a surveyor's assistant on federal surveys along the Mississippi. He gained a practical knowledge as a surveyor, which he would then bring to his astronomy, at least to his teaching astronomy later on. So landing at the University of Michigan put him immediately into what was eventually would be called the Ann Arbor School of Astronomy. The University of Michigan was the observatory at the University of Michigan is confusingly called the Detroit Observatory, although it's at Ann Arbor. And that observatory was a very important part of American astronomical history, because it's where a German tradition of astronomical instruction was picked up and implemented by this guy, Franz Friedrich Ernst Brunov, who was brought to Michigan by Henry Tappan, the president of the University of Michigan. Now, this is in the 1850s, early 1860s. This is exactly in the period, this is before our observatory even existed, of course, but this is exactly in the period when a number of American universities are importing German methods of instruction in a lot of ways. The whole idea of a research university was modeled on German universities. And Tappan was a big supporter of this, just as some years later here John Bascom would be, and that would turn into our observatory. So Tappan was the one who brought Brunov from Germany to run the Detroit Observatory at the University of Michigan at Ann Arbor. One of the most famous members of that school, and very important to Comstock, was James Craig Watson, who was originally Brunov's student, and then was Brunov's successor as director there. There are a number of other important astronomers one could name who come out of the Ann Arbor School, but one that is frequently named, probably because he's the most famous of any of those, is Asaph Hall, even though he was only there at Ann Arbor for about 3 months in 1855, studying with Brunov. But Asaph Hall, this was still in a day when you could pursue an astronomical career without necessarily having a degree in astronomy. Hall was talented enough, he got picked up at the Naval Observatory fairly quickly and became famous there, discovering, among other things, the moons of Mars. So Asaph Hall is a famous member. There are a number of others. Shaberly, who was very influential on the foundation of Lick Observatory and later back at Michigan, and a few others. In fact, there's quite a long list. There's a nice little article that was done about this Ann Arbor School, and it claims that something like half of the trained astronomers working in the U.S. in the late 1890s were trained at Ann Arbor. So that's the Ann Arbor School, it's sometimes called. And so, of course, this is Comstock's background too. He got his training under Watson there at Michigan and got a degree, got his undergraduate degree there at Michigan. And then, as you probably know, in 1879, the University of Wisconsin had a new observatory and hired Watson to come here to Madison as its first director. Well, that's how Comstock got here as well. Comstock was basically Watson's assistant there at the Ann Arbor Observatory when Watson was hired to come here to the Washburn Observatory, and basically Comstock came with him in the fall of 1879. Now, as things would fall out, Watson didn't last very long. Watson died suddenly in the fall of 1880 after having taught one academic year, basically, in Madison. And at that point, it really fell to Governor Washburn to find a replacement for Watson. This is where the beginning of connections that will crop up again and again to the U.S. Naval Observatory start, because Washburn, he had obviously poached Watson from Michigan, but he went to the U.S. Naval Observatory to try to convince Asaph Hall to come here as director. Hall was not interested. He tried to get recommendations from Simon Newcomb, who was a preeminent astronomer out there in those days, and Newcomb recommended his assistant, Edward Holden. And Holden, Washburn took that recommendation, hired Edward Holden as director here. Holden started corresponding with Comstock, who had kind of been left as the student assistant at the death of Watson, had been left to oversee an incomplete observatory. The building was still under construction, although the equatorial telescope, the 15.5, was under construction, but the rest of the observatory was more or less incomplete. Holden immediately starts corresponding with Comstock before Holden moves to Madison, and for a month or so, Holden is kind of running the observatory through Comstock, and having Comstock act as his agent here and sending Holden information about the state of things and sending back decisions on, add the gas lighting in the library, but don't put it into the student observatory and things like that. And then Holden came here in the spring of 1881, and Comstock was kind of automatically his assistant astronomer. So Comstock's career at Washburn goes back to the very beginnings, coming here with Watson when the building was still incomplete. Comstock continued to be deeply involved in the running of the observatory, in part because Holden traveled a lot. Holden went off, for example, from March until June in 1883 on an eclipse expedition into the South Pacific, left Comstock in charge of the observatory while he was gone. Comstock, however, was not at all confident that he would be able to make a career in astronomy. So he took his time working for Holden here to go to law school. thinking that this was something that at least you could fall back on if you can't make a living as an astronomer, and graduated from the UW Law School in 1883. Apparently for a little while considered setting up a law office in Minneapolis or maybe St. Louis. There's a little bit of correspondence about that. But he kept on picking up jobs in astronomy. In particular, he ended up at the U.S. Naval Observatory for a little while in 1884, working for Simon Newcomb, where Newcomb tried to hire him. There's another, this sort of pattern goes on too, that people seem to notice that Comstock is this up-and-coming young guy and they want to put him on their staff. So Newcomb offered him a job at the Naval Observatory, but he turned that down for reasons not entirely clear. Maybe he just didn't like the work, because he turned out to be a very active, observing astronomer, and his work probably at the Naval Observatory would have been a lot of computation. That's what he was doing for Newcomb in that year. They're working on the orbit of some asteroids. He ends up back in, after that stint at the Naval Observatory, he ends up back in Madison, where Holden has found a way to keep him. Holden found funding, basically private funding at first, from a lumber guy up in Eau Claire, a guy named Ingram. I have no idea how Holden met Ingram, but Ingram agreed to fund Comstock for a while, fund Comstock's salary. Then a little bit later on, Holden also got some money from the National Academy of Sciences to fund Comstock. So he's piecing this sort of together. You can see why Comstock might not have been all that confident that he would have a career in astronomy. And in fact, by the fall of 1885, he had taken a position as a math professor at Ohio State University. About the same time that Holden left, later that fall, Holden accepted the University of California's offer to come to California, ultimately to become the director of Lick Observatory. Holden had been deeply involved in the development of Lick Observatory for a long time, and the trustees at the Lick Observatory didn't want to lose him. They wanted him to be director, but the observatory wasn't ready, so they convinced the regents of the University of California to hire Holden as president, so that they would have him there, and then as soon as the observatory was complete, then he would become the director of the observatory. So they still joke out there that Holden was promoted to director of the university, which means that of the observatory, promoted to director of the observatory, which means the director of observatory at Lick outranks the president of the University of California. Well, the Washburn Observatory was left without a director. And so this was a, excuse me, there was sort of an interregnum during which, again, sort of as Comstock had during Holden's absences, some other students effectively ran the observatory, and very competently. Milton Updegraff and Alice Lamb and a few others managed to run the observatory and produce some publications, actually not under the nominal leadership of a physics professor. But the regents eventually, after again trying to recruit Asaph Hall and some others as director of Washburn Observatory, ended up with the idea that they would offer Comstock the job. But clearly they weren't quite, Comstock was still fairly young and inexperienced, or at least maybe they saw it that way. He was pretty experienced astronomically by that point. But he was offered the position of associate director of the Washburn Observatory under the condition that Asaph Hall of the U.S. Naval Observatory would be consulting director, so that the two of them would do this job together, a more senior astronomer. And again, at about this time, Holden is trying to hire Comstock to come out to Lick. So there's a bit of correspondence about that. It actually turns out that the University of Wisconsin offering Comstock $2,000 a year was paying him more than Holden could pay him at Lick. And Comstock at that point is partly helping support his family, his parents, all of whom moved back to Madison with him. So he needs the extra money, he says in the letters to Holden anyway. I can't take that job because you can't pay me enough. And he was then associate director in August of 1887, getting $2,000 a year with Asaph Hall nominally, well, not nominally, actually supervising and advising on the work for $1,000 a year. That connection to the Naval Observatory had been strengthened during this interregnum in basically 1886, when the regents, not really knowing what to do with the observatory, and becoming aware that the U.S. Naval Observatory was relocating from their original location to a new location, the current location of the U.S. Naval Observatory in D.C. And they had, so their telescopes were out of operation while they made this move. The regents offered to the U.S. Naval Observatory the use of the Washburn instruments, which is kind of interesting because they were being effectively used by the students here. But nevertheless, that worked out, as I'll mention in a minute. The Naval Observatory, at least one Naval Observatory astronomer did actually come to Madison to use the observatory to continue some work that had been ongoing at the Naval Observatory. But the work with Asaph Hall was influential too. I'll mention a little bit later, at least one program that we know that he specifically recommended to Comstock that became important. But by July of 1889, the regents had decided that they were confident enough in Comstock to make him director in his own right, and he got a raise to $2,200 a year, and Hall, of course, now was not consulting director anymore, so I don't know where that extra $800 a year went, but it didn't go to Comstock when he got the job. So now Comstock is in charge at the observatory, and there really had not been much of a staff. Holden had had some assistants, one of whom was Comstock, students at various points along the way. But there, except for very short periods of time, there had never been more than one astronomer at Washburn Observatory. And at this point, there's still only one actually on the payroll, and that is Comstock. But there was the U.S. Naval Observatory astronomer Stimson Brown, S.J. Brown, who was a meridian circle specialist at the Naval Observatory, but that work was being interrupted because of the move out there. He came to Madison in October of 1887 to begin using our meridian circle to carry out their program of improving a certain set of star positions. This was sort of perpetual work at the Naval Observatory, improving star atlases and star positions, ultimately for navigational, but also astronomical purposes. There was also some student help available at that time, and by that time I mean really up until the middle 1890s, because the observatory made some money from selling time signals to the railroad, which I've talked about in other contexts before. But its importance at this point is that it brought in cash that could then be used to pay student assistants. So they would have a few student assistants. This dropped off pretty quickly. By about 1900, there was basically no more cash. There was still a time service, but the only customer was the university. The observatory clocks were ringing bells in the classrooms on campus. And the only real uses for the timekeeping were the scientific uses at the observatory and the bells on campus. So that wasn't bringing any more money. And during a good bit of Comstock's career, he seems to have no student help, or very little. There are many times when he refers to the rigors of observing that the observer has to do all this work with the dome and the telescope, and then that affects your observing abilities and what they used to call your personal equation. So it sounds like he's working alone. It sounds like he didn't have much student help along the way. He did hire computers, though, people to help with computing, at least from time to time. Well, Brown, Stimson, S.J. Brown was here as it says here, until October 1890. But somehow or another, Comstock got money from the state, apparently not the university, but from the state, to add a staff position at the university and at the observatory. And so in November of 1889, he was able to hire Albert Flint, a meridian circle specialist from, guess where, the U.S. Naval Observatory, to move to Madison and take over a research program that Asaph Hall had suggested, which I'll mention a little bit later. Here you see Brown. He's the one on the left as you're viewing it there, and that's Flint on the right. And below there is the Repsold meridian circle, which Washburn had bought for the observatory. Basically, the installation and operation of this in late 1882, when it became operational in late 1882, basically was the completion of the observatory, the last major piece that Washburn paid for. A meridian circle is a very special sort of instrument that we don't see anymore in astronomy. I think it's safe to say. I don't think there are any working in the world. There were until a few years ago. There were some robotic ones, but I don't think even those are working anymore. This is a very special type of telescope, and it takes a very special observer to work with it. It's primarily a transit instrument, which means that the astronomer observes the passage of a star through the field of the telescope. The telescope is mounted so that it only observes along the local meridian. So basically it's mounted on an axis that goes east-west, and so the telescope can only pivot north and south. So if it's mounted properly, then when you're looking through the telescope, you're looking at the local meridian. When the sun crosses the local meridian, that's noon, you can see stars, not that they use that telescope that way, but you can see stars when they pass through the field of the telescope. When it crosses that wire in the middle, then presumably it's on the local meridian. So you notice that time. You mark that time very carefully. Actually, in more practical terms, you can see there, just in this schematic, which is from a textbook, not a real instrument, there are 5 wires in there, and they would mark the time, typically electrically by those days. The observer is looking through there and sees the star crossing the field and pushes a button every time it crosses one of those wires, one of those fibers, and you would derive from that a time at the meridian. And then if you did that with, say, a second star a little while later, the time difference would give you the east-west difference between those distance between those 2 stars. So you can measure very accurately the east-west coordinates of a star. A meridian circle is a transit telescope, but this is a small transit telescope that was in the student observatory. It's right in there in our exhibit hall in there. But this is not a meridian circle. Let me go back. I should have grabbed a laser pointer here. So this is a transit instrument. It pivots on this east-west axis along the meridian, but there's an extra, of all these circles, which are a little bit hard to parse out, there's one right here, which is very carefully calibrated and adjusted so that you can also measure pretty accurately the altitude of the star along the meridian when it crosses. And so you can also get, in addition to the time of the passage, and get an east-west coordinate, you can measure its altitude above essentially the southern horizon, well, not the southern horizon, its altitude above the horizon at transit, and then you can convert that into a north-south coordinate. So the meridian circle could do those 2 things, but meridian telescopes were used for a lot of other things as well. Transit telescopes, I should say, were used for a lot of other things as well. And so measurements with transits were an important part of education for astronomers in those days. So that's the one from our student observatory there. So I'll come back to the meridian telescope in just a minute, because Asaph Hall did a major program, well, several major programs, but I'll come back to that. Comstock had then Flint working on the meridian circle, and Comstock preferred to specialize, although he had plenty of experience with the meridian circle. Comstock preferred to specialize in his work on the equatorial. He was working on double stars from really the very beginning. He reports in October 1887, when he's still very new to this director job, that he's been experimenting with with the best ways to make double star measurements. So this means looking at two stars that are really close together and measuring their separation and measuring the angle that connects the two stars. Most of these turn out to be binary stars. There are a few that are accidental alignments, but most of them turn out to be binary systems, though this was not known at that time. But they wanted to discover binaries. They wanted to look at double stars. Some were known. A handful of true binary systems were known, going back actually to William Herschel, who demonstrated, I think, the first ones. Comstock wanted to pursue these kind of measurements, and you need the equatorial telescope to do this, and you need another kind of micrometer, like the one that was measuring the passage of stars along in the field of the transit telescope. You have another kind of micrometer on the eyepiece end of the telescope there. That's our telescope on its original mounting as it came from Clark in 1879. So he's starting to work on double stars, and that will continue to be an important part of his science for quite a few years. But he also, by November of 1877, there's some interesting letters. He's making inquiries to the firm Warner and Swasey, who made telescope mountings in those days and specialized in other sorts of relatively heavy-duty astronomical work. He writes to Warner and Swasey about modifications that he would like to have made to the student observatory dome. And that will be for this project that he is contemplating when he visits the optical shop of John Brashear, who was a telescope and instrument maker out there in Allegheny, Pennsylvania, to discuss the fabrication of something called a Lowy device, which I'm going to talk a bit about here in a moment. In preparation for that work, he also makes an application to the appropriately the Watson Fund of the National Academy of Sciences so that he can pay Brashear to build this device. And he's also shipping the 6-inch telescope from the student observatory out to Washington, D.C. to the firm of the Fouth firm, where their instrument maker Segmuller modifies the 6-inch Burnham telescope that's still on the roof of Sterling Hall to this day to accept this Lowy device onto the front of it. So what is this? Well, what he's doing here is something that nobody else in North America did. In fact, hardly anybody else ever did this except for Lowy himself back in Paris. There's the student observatory. Nice picture of the student observatory there as it was originally built with a dome, and inside there is the 6-inch Burnham telescope. This project here required a major modification of that dome, and that's what Comstock wrote to Warner and Swasey about, although apparently he eventually had the work done locally. I can't find any evidence that he actually did get Warner and Swasey to do the work. They probably wanted too much money. You see what's happened to that dome there? It's been modified so that the two hemispheres of the dome have been split, and one of them has been modified so that it can fit into the other, sort of a nest or a clamshell kind of arrangement there. So that instead of looking through the typical narrow slit of an observatory dome, he's got half the sky available to look at. And that's because, as you'll see in a moment, what the Lowy device does is measure very large angles on the sky. Now this work, as I say, it's unique in the US. It gained a lot of praise and produced some original results. It's really kind of one of Comstock's first major research contributions. And it was ready to go sometime in 1889, apparently, when he developed some kind of eye problems that are described in the correspondence as iritis. I don't have any idea what that actually amounts to. And there are mentions of surgery. Now, I don't know what optical surgery was like in the 1880s, but I don't like to think about it. He couldn't then, because of that, he couldn't begin observing until after his eyesight had recovered, and then there was the academic year that came along, and then he had travels in Europe planned, and so in the end he didn't actually begin this program until September of 1890, and it was completed by then summer of 1892. So what is he doing? He's measuring two fundamental effects that positional astronomy has to have a handle on in order to get accurate positions of stars in the sky. The two effects that affect the apparent position of a star are what's called the aberration of starlight, and the other effect is the refraction of light by the Earth's atmosphere. So the refraction we actually see all the time without thinking about too much, but when you see the sun setting on the horizon, if you draw a line from your eye, a geometrically straight line out there, it actually won't point at the sun. It'll point off into space because the sun is already below the horizon. The light is being bent around by the Earth's atmosphere into your eye. So if you think you're measuring the position of the sun, you're not, unless you take into account refraction. So the same thing happens to stars. It basically makes everything in the sky refraction. Refraction of the atmosphere makes everything in the sky a little higher than it should be, but it goes to zero at the zenith. So how does it behave in between? Well, that was a problem for astronomers. It had been tabulated, studied by in Europe. There were a couple of standard tables that astronomers used to correct for this atmospheric refraction, which hadn't ever even been touched. Tycho Brahe was actually the first one to make a refraction correction. So to measure that, what he wanted to do, it's zero high above, but it increases as it goes to the horizon. He wanted to be able to measure the differences, the angular differences between stars, one high above and one near the horizon, and then say compare that when they're at the same two stars across a different arc, but a wide arc, when they're at the same altitude above the horizon. And by studying many combinations of stars across lots of different arcs, build up an understanding of the refraction as a function of altitude. The other effect is the aberration of starlight, which is a periodic shift in the apparent position of a star caused by the Earth's motion in its orbit. It's not stellar parallax, which also shifts on an annual basis the apparent position of stars. It's a much bigger effect and had been known since 1727. James Bradley discovered that, and it was the first evidence before stellar parallax was detected. It was the first actual physical evidence of the motion of the Earth around the sun, the Copernican motion of the Earth. But its amount had been studied in a number of different ways, mostly by looking at the deflection of stars at the zenith. But it was becoming recognized in this period in the 1880s that the Earth's North Pole, the actual rotational axis of the Earth, there are a number of motions known. It's known to precess, and it's known there's something called nutation. How fine a motion, how fine are the disturbances in the motion of the Earth's axis? If you're measuring your star positions based on the horizon and the zenith, then latitude variations, what that was just called the variation in latitude, widely discussed, various theories about how it might be changing, that's going to affect it. If you don't understand the latitude variation, and there was a great deal of debate about that, then you don't have a good handle on altitude measurements, on horizon and zenith measurements. So Comstock, using the Loewy device, was going to look at stars across the sky, differences in the aberration as a function of position on the sky, and these would be differential measurements like the refraction measurements, so it would be independent of any latitude theory. You could just you don't have a latitude theory, you just don't have to pay any attention to it, and you can still get a number for the aberration of starlight. The Loewy device was designed to do this kind of thing by Loewy, who was at the Paris Observatory, using, in effect, an optical trick where you have a prism or mirrors arranged in a configuration like that. So your telescope is looking at these two faces, but the light, the stars that you're seeing there are separated by a very wide angle that's determined by the angle of the prism or the mirrors there. So the way Comstock designed his, there were 60-degree angles of the mirrors, so the stars were 120 degrees apart. And if you're sure about that 120 degrees apart, then you know that the difference that you see in the eyepiece is 120 degrees plus or minus whatever their actual separation is in the sky. So by measuring in the micrometer the separation of these two stars, he could get, at the precision of the micrometer, he could get very wide angle measurements. So that's what he was using the Loewy device for. And the work was pretty successful, far from earth-shaking. In the first place, all he's really doing is delivering more refined numbers that people will use in reducing their data. So no important physical insights coming in here. Basically, his results confirmed earlier values, but at higher precision. They were the first measurements of either of these effects in North America. Whether it's reasonable to expect the refraction might be different in North America or not, it's an open question, but it turned out that it wasn't significantly different in North America. It was the first time that anybody had taken into account certain effects like the humidity of the atmosphere and the colors of stars and the magnitudes of stars, which affect how astronomers measure positions when they're using their eyes. This brought him to some prominence. There I've quoted Loewy, who a few years later, in an address to the Académie des Sciences in 1896, the sagacity and perseverance of which Mr. Comstock has given proof in the course of these difficult researches seems to me to designate his work as particularly worthy of the attention of the Academy. He corresponded with Loewy about the work, and he ended up producing far more data than Loewy ever did using this type of instrument. So he's using an instrument that really nobody else, certainly nobody in North America, and probably only Loewy had ever used, which he designed and financed on his own here and then carried out through an important research program with it. So that's pretty typical of Comstock, instrument innovation and dedication to long hours of hard work, which really come to the fore in the double star work. Double star measuring at Washburn had begun with S.W. Burnham in 1881. Burnham was famous for discovering double stars, and then when Burnham had access to bigger telescopes with fancier equipment than he could afford, measurements of these stars, that is the position, the angle, sometimes only a few arc seconds or less between these two stars, and the angle that the two stars make with respect to the coordinate system. So you get enough of those kind of measurements and maybe you can figure out the orbits of these things. Well, in the case of Comstock, or everybody else in this period, they're making these measurements with the human eye, looking through the eyepiece of that telescope. And astronomers were always very concerned about something called the personal equation, which enters in various ways into these sorts of things, but basically is a quantitative approach to the human errors of observation. How do we tend to overestimate or underestimate or anticipate a timing measurement? Everybody is maybe a little bit ahead or a little bit behind somebody else. And the personal equation is important, but if it's the same, then it's something that you can understand systematically. And the theory, at least, was that the same observer using the same instrument over a long period of time minimize the errors of the personal equation. So Comstock deliberately set about to do this, to spend decades observing the same double stars over and over again, which was done, as I mentioned, with a micrometer at the end of the telescope. Governor Washburn had bought, when he bought the telescope from Alvin Clark and Sons, he also bought a micrometer from Alvin Clark and Sons. And although we have one filar micrometer from the old observatory equipment. Unfortunately, I have no idea whatever happened to our Clark micrometer, but this is at the end of the telescope here. This is actually attached to the telescope up this way, and the astronomer looks in the eyepiece right there and sees a pair of stars. He also sees in front of the stars at least a pair, maybe more than one, of fine threads that are illuminated by this lamp up here. And by rotating this knob right here, one of the wires can be moved relative to the other wire. So you rotate the whole thing around its axis. It rotates around this way until the wire that goes across that way lines up across the two stars. And then you rotate here to get measure the spacing. And by calibrating the screw that's moving those threads, you can figure out how many arc seconds apart those stars are. And then by reading the scale around the edge here, there's a vernier there, the position angle. So you get two numbers. You get the separation and you get the position angle. By the way, I pointed out the lamp because this doesn't look like any other Clark micrometer because Burnham modified the Clark's way of illuminating the threads with a little oil lamp right there and a mirror here. All this other stuff that looks a bit like a jigsaw or something, Burnham figured out a way to keep the illumination angle the same on the wires no matter the orientation of the micrometer because the illumination angle will change where the stars apparently are, where the threads are with respect to the stars, introducing error. So our micrometer, wherever it's gone to, was unique by being modified by Burnham for this purpose, away from the Clark's design, although it was copied out at Lick as soon as Burnham published it. Comstock is starting in on a decades-long program of observing a list of about 170 odd stars, in which he reports in his final analysis that each one is at least 100 settings on each star. So that's a lot of measurements done over the years with the micrometer at the telescope over those decades. And one other part, as he went along, so he's measuring the properties of the double stars, but when there was another dim star in the field, he would measure the distance of that dim star from those stars, and that will crop up again in proper motion studies that we're about to get to. So he was really compiling data for sort of two projects as he went along there. Well, so the scientific goals of observing binary stars are pretty important. Ideally, you get from the positions of the binary stars an orbit. You get the orbital period, and you get in angular size the size of the orbit, maybe. But there's a lot of things you don't know about this, like how is the orbit tilted with respect to the observer, and we don't know just starting out how far away those things are either there. Here's just an example of an orbit, and this one is much better defined than a great many of them. There's some of them where you wonder how they could possibly see the orbit in there at all. But here's one. This is a published one from an atlas of these things that we had at the Washburn Observatory, that they had at the Washburn Observatory there. That was published by an astronomer named C, TJJC, of this star Zeta Boötis here. And I've put in the dates because they're more easy to read than the little tiny numbers there. And so you can see why it takes decades to try to gather this sort of data. And then C had published this orbit using not, of course, his own, probably some of that might be his data, but mostly other people's data. And then you can see where the data points are, and then he had sketched in and completed the rest of the orbit as he saw it. The penciled in markings are Comstock's in our copy of this book. And so you can see that C was wrong about this orbit, which he was kind of, in those days, he was kind of doing a seat of the pants kind of fit of these things. The quantitative methods of doing this were coming along, more rigorous methods of doing this were coming along. But Comstock there is getting, when the data runs out there in 1895, Comstock has been continuing to accumulate data on this pair of stars, and you can see 19, 10, 12, 15, and so on coming along there. So he's sketched in an alternative orbit to C's. So we don't have this for all the stars that Comstock did, only for a few, and the few that he published. Mostly what he did was publish his observations so that they would be on the record for C or anybody else who is going to take these sorts of numbers and calculate orbits of binary stars. Henry Norris Russell became really big in this just in the next generation of astronomers, and data like Comstock is compiling was essential to that kind of, that sort of work. So you get the orbit, maybe, and then if you can get the distance, then you can figure out the actual size of the orbit. And if you have the period of the orbit and the size of the orbit, then you can determine the mass of the stars in the system. And if you're careful about it, you can make some estimates about the individual masses of the stars, because they're not necessarily equal, in fact, seldom are. And if you have a distance, you can get some rough luminosities of the stars. So this all sounds extremely primitive to Joe, who's an experienced stellar astronomer sitting right there. But these are the first real numbers that are coming out about star systems is coming out of these very early binary star observations, of which Comstock was a major contributor. It fills the double star observations fill the whole volume of the publications of Washburn Observatory in its final form. That is in the final form of this data, which was published in about 1919, right towards the end of Comstock's career. Another bit of science that he did while observing double stars was to use them to test the idea of whether the moon has an atmosphere, something that had been kicked around a fair bit. And Comstock used the occultations of binary stars, doesn't matter if they're binary doubles, but double stars, I'll say, by the moon. He would measure with his micrometer the spacing between the stars as the limb of the moon approached. And if the moon had an atmosphere of any appreciable amount, then it ought to refract the starlight as well, just like our atmosphere does. He ought to be able to see a refraction effect affecting the spacing of those two stars. He saw none, which allowed him to put an upper limit on the stellar, on the lunar atmosphere. So this was a good test of whether the moon has an atmosphere or not, and a different application of observing double stars. All right, I alluded to this a couple times. So I'm talking here about decades of work that Comstock has been doing with double stars using the equatorial telescope. Asaph Hall had suggested in the very early days that an appropriate use of our Repsold meridian circle would be to measure stellar parallaxes. There was a particular method that Jacobus Kapteyn, the Dutch astronomer, had recommended, and Hall was saying, follow Kapteyn's method and do a survey of stellar parallax with your meridian circle. Basically measuring as accurately as possible positions of stars on the sky and watching them shift during the course of a year as the Earth orbits around the sun, and then across this baseline, depending on the distance of the star, it makes a small angular motion, and you can calculate from that angle how far away the star is, how far away it really is. Well, this was really important work and was extremely difficult work because the angles are very small. It also is an unusual astronomical pattern, so you usually think about the astronomer Comstock for observing double stars. Basically, he's spending the whole night up there looking at double stars that are accessible at that time of the year and making his measurements. But for Flint to do this work, he basically was looking at stars that were kind of at right angles to where he was looking at stars in the early evening and in the early morning. And when the Earth is over here, in this part of the orbit, at this time of the year, it's not a good time to measure the parallax of this star. you want to measure this star when it's near the, in the morning, and, well, in the evening rather, the way this diagram is drawn, in the evening and in the early morning. So Comstock would go in the evening right after dark, do a few hours of observing until about 9 p.m., then leave, come back early in the morning, like 3 a.m. or something along that line, and observe the early morning stars to put together his parallax sets. So he did that for quite a few years along the way with the Meridian telescope. He did a series of these in 1893 to 1896, and then they made some technical improvements, including a new kind of filar micrometer, and also Comstock, again, exercising his instrument building skills. Comstock had decided that maybe the accuracy of the position measurements on the meridian circle would be improved if instead of looking at a point image, you looked at a diffraction pattern of a star as it's crossing the field. And so he built a thing that goes on the meridian circle that was a little bit like Venetian blinds that caused the star image to be a diffraction pattern. And Flint, using that method and the new micrometer, did a second series of parallax observations in 1898 to 1905. So not many stars were actually measurable this way in that period, maybe 100, probably not even 100, depending on what limits of accuracy you want to put on there. In Comstock's, in one of Comstock's textbooks, he prints a list in 1901 of stars of known parallax, and there are less than 50 on the list. Many of those had come from Washburn Observatory. In fact, in those days, about half of all the known parallaxes of stars had come from Flint's work at Washburn Observatory. And knowing those parallaxes was really important because of the attempts to understand the stellar universe, what we might now call the galaxy, although that term is a little anachronistic in that period. What is the distribution of stars that we live in when we look around us? Is the sun near the center? And how far away, how far into space does this cloud of stars that we seem to be living in stretch? Well, it would be, you could test that if you could measure the distances to stars. But we're talking hundreds of thousands at least of detectable stars in the sky around us, and you've got maybe 50 to 100 parallaxes. It's not going to tell you much about and those are all nearby stars anyway. It's not going to tell you much about the distribution of stars. So astronomers engaged in a statistical exercise, or I should say a statistical program, of which Jacobus Kapteyn at Groningen, I think, in the Netherlands, and he was in the Netherlands. Kapteyn created a concept called statistical parallax, or at least that's what we call it, in which he made some assumptions about average proper motions of stars of average magnitudes, so that you could measure, so the proper motion of a star is how much it appears to be moving across the sky, and the nearby ones zing along pretty fast, and the more distant ones move along kind of slowly on the average. So if you assume that you can average these sorts of things with distance, then you could look at the proper motion of a star, of a dim star, and say, well, statistically that star ought to be this far away from us. And then you can survey the sky, which Kapteyn was doing photographically. Well, he was using other people's photographic plates, looking at the sky, analyzing the brightnesses of star fields and densities of star fields, and trying to get proper motion numbers, and using those proper motions to estimate distances into the universe around us, into the stellar universe around us. I've tried to read some of these papers, and I got to tell you, they're pretty dense and hard to follow. But the general idea here is that proper motion is a proxy for the actual distance of these things very much on the average, averaging everything over here. Well, Kaptein's data was pretty much based on observations of stars that went down to about 8th magnitude, which is a lot of stars, but not a huge number of stars. If it's a statistical problem, then the bigger your sample, the more interesting, the more useful your results are likely to be. In Comstock, it occurred to Comstock that there were available a list of observations of relatively faint stars between 9th and 12th magnitude that had been made in the 1830s by Otto Struve at Pulkovo Observatory in Russia. And nearly 50 years had passed. So Comstock's idea was go back and reobserve Struve's list here and detect the proper motions of these dim stars, much dimmer than Kaptein was working on, and so extend that work. He measured the proper motions of 222 of these stars between the 8th and the 12th magnitude, and this is where a lot of the data he had gathered observing the doubles, the distances of dim stars from those doubles, is gives you information about the proper motion of those dim stars in that neighborhood. So he came up with sort of a surprising result, which was that of those dim stars, the average proper motions were something like triple what Kaptein's model was predicting. Those dim stars seem to be moving much faster than you would expect them to move. So something is wrong with Kaptein's theories, and Comstock publishes this work in a number of papers starting in 1904, sort of some preliminary results, but the preliminary results actually provoke a reaction from Kaptein, which provokes a reaction from Comstock, and they get into a little bit of a feud. It's a polite feud carried out with great respect in print between the two of them, criticizing each other's conclusions and practices. But to try and shorten it up here, basically, Kaptein said that the stars in this sample that are moving faster than they should be moving must be nearer to us. But these are very dim stars, 9th to 12th magnitude. So if those stars are close to us, but still very dim, then they must be much dimmer than your average star, maybe a sun-like star or something along this line. So he suggests one possibility here is that most of the stars in the sky, because we're talking about large numbers of stars when we get to 9th through 12th magnitude, could be a population of dwarf stars, that most of the stars in a given region of space might be very, very dim stars, these so-called dwarf stars. Another possible explanation, though, is that that space is not perfectly transparent, which is something that Kaptein had posited as part of his theory. Comstock pointed out that the numbers that he's getting out could also be explained if there's a certain amount of absorption of light in interstellar space, if space is not transparent, or some combination of both of those effects. And it was over all those sorts of things that Comstock and Kaptein debated until about 1910, when Comstock kept on publishing them, but Kaptein just stops talking to him, apparently. But both of those things are, in fact, right. Comstock had uncovered some of the first evidence that the vast majority of stars are dwarf stars, these dim M stars out there. They're far more numerous than the brighter stars. And it was those proper motion studies that made it apparent, gave evidence that the stellar population seems to be like that dim stars are far more common than bright stars. And he was also right that there's interstellar absorption, although it's not clear that his results were actually a measurement of the stellar absorption. But he was right in arguing that you have to think about taking that into account, and that would become much more important than in the work of his successor, Joel Stebbins, in the next generation. But Comstock was out there on that issue from the very beginning, and I should say from the very beginning, providing some evidence that this is an effect that we have to take into account. And it also shaped a theory that he put out, and he did publish this. And although it's a very qualitative sort of idea that's fascinating in part because it shows how important this problem was to understand the stellar structure of the universe, something that by the 1930s would begin to take on the kinds of picture that we sort of think of now with where we are in our galaxy. Comstock's idea was that because there is this interstellar absorption, or at least it looks like there's interstellar absorption, that space is not transparent, that this effect might actually explain why we have the Milky Way, which is a problem that goes back to antiquity. The Greeks used to wonder about this. Why aren't stars just randomly sprinkled across the sky? Why instead do you have this thick band of starlight that stretches across the sky? What's going on here? Is there a belt of stars around us or something? What is this effect? And Comstock proposed that this effect, that we see this Milky Way thing, because this is our local cloud of stars, many light years across, tens of thousands of light years across. But it's surrounded by a dusty chaos of material. And there's motion. He thinks that this cloud of stars, that the sun and most of the stars that we see around us in the Milky Way, is moving through this dusty chaos and actually clearing the way in some sense, maybe gravitationally or something. So we see farther away along the plane of the Milky Way, and so we see lots of stars when we look in that direction. But out here, where there are things like spiral nebulae, those are clouds of obscuring matter out there. So the obscuring matter becomes very thick in Comstock's view, stretching away from the plane of the Milky Way. So we see the sky's darker, we see fewer stars out there because we're looking out into that dusty chaos. So he's got it almost exactly backwards from the modern view, that we look across here and we're looking through this dusty material, and we look away from it out here and we're seeing out of our galaxy there. But this was Comstock's attempt to make sense of the data that he was getting from his absorptions and proper motion studies. Well, I'm going to have to wrap up here, but I want to talk about just a few other aspects of Comstock's career. He was very important in the founding of the American Astronomical Society, which was originally called the Astronomical and Astrophysical Society of America before 1914. Comstock wrote the bylaws for the first, so he sat up there at Washburn Observatory at his desk and, using his legal training, wrote the bylaws for that organization and became its secretary for the first 10 years of its existence. He chaired the organization's committee on Comet Halley observations. Then he served as after 1914, the AAS, he served as its vice president and then as president elected president in 1925, was president, and Joel Stebbins was secretary when they organized the first meeting in Madison of the AAS in 1927. Oh, this is, let's see, oh, here's Comstock right there, president of the AAS when they met in 1925 up there in Northfield. There's Joel Stebbins sitting right next to him there. Let's see, should I use the, yeah, here's the pointer. You can see that, right? There's another Wisconsin astronomer in there, John should have written it down. It was a student observatory at Washburn in Comstock's early days, but became a successful insurance executive out in New York City. Didn't have an astronomical career at all. Let's see. There's Fott, who worked with Stebbins at Illinois. Oliver Lee, who was at Yerkes, and quite a sprinkling of women who I'd love to identify, but they're actually a fairly large fraction of the group who's meeting there up there at Goodsell in Minnesota. Comstock was the first UW faculty member elected to the National Academy of Sciences. He was also engaged in a running lasted quite a few years, an attempt to reorganize the U.S. Naval Observatory, which of course he knew well. The astronomical community was really annoyed that it was run by naval officers who couldn't possibly supervise astronomers properly, and they had legit criticisms of the astronomical productivity of what they wanted to be called the U.S. National Observatory. They wanted to rename it. They wanted to put a civilian in charge. Comstock was part of the first attempt to do this back around 1899, which was thwarted in Congress, and Comstock was obviously an anonymous complainer to the congressional committee who's working on it, accuses Comstock and company of trying to take over the Naval Observatory from them. There were subsequent attempts that also never went anywhere, but Comstock was always prominent in organizing these sorts of these things. The trying to produce a national observatory long before we actually had a real one. Was also very active in teaching and outreach. He taught astronomy courses during his whole career. And then when Charles Van Hise decided that graduate studies needed to be organized, he put Comstock in charge of a committee to try to coordinate and set standards for graduate education, for advanced education beyond the bachelor's degree. Comstock then led that as it was eventually developed into a school when he became the dean of the graduate school. This was a guy who didn't have a PhD and liked to occasionally point out that he had a certain amount of challenges in supervising the production of PhDs since he didn't have one himself, although some honorary degrees fixed that along the way. He got honorary doctorates from Illinois and Michigan, so at least he had the wallpaper at a certain point. He also was very active with UW Extension, traveling all over the U.S., and also published a number of books. I have a copy of his introductory astronomy textbook here that I'm going to read from briefly in conclusion. And also the public visitor nights, which they consistently did. In the observing books, it always says Wednesday night visitor night, and Flint and Comstock took turns doing this. No student helpers, apparently, during that time. Comstock himself was, at times, there are people who refer to him as being sort of an intimidating kind of figure, whether this is just intellectual intimidation or it really was an intimidating guy. I don't really know, except that all of his colleagues refer to his good sense of humor. But he certainly had little patience for foolishness. There's a great story from the days of Comet Halley when there were long lines of people wanting to see the comet up at the observatory. Comstock introduced a ticket system in order to try to control the crowds, and got permission from the president of the university to charge a nominal admission charge. And apparently Stebbins writes that Comstock received a phone call one day at the observatory demanding to know what the astronomers were going to do with this money they were collecting for viewing the comet. And apparently his answer was, "We're going to buy a new tail for Halley's comet," and hung up the phone. I also found a little clipping in the newspaper from 1919 where apparently there was a flap. These things happen, don't they? From time to time, the planets all line up somewhere and people go a little nuts. Apparently in December 1919, most of the major planets were on the far side of the sun. There's a little article in the paper where they've gone down to check with the astronomer. They talked to Professor Comstock, whose response is, "It's all a fake. There's no more reason for the planets crossing behind the sun at the same time than for all the children of a school to go out the same door. So there's nothing to this alignment here. It's all a fake." Well, he worked until 1922, although his last year of work at the observatory, he was basically keeping the business going while Joel Stebbins, who had been hired then to succeed him, set up his own research programs, which were radically different from what Comstock had been doing. He had a small family, one daughter, Mary, who was the only child ever brought up on Observatory Hill. After he retired, he and his wife, who's there, Esther, there she is, took a world tour. There's only one photograph I can find of their travels, although there are letters from them at various places around the world as they made their loop around from first through Asia and then back through Europe that way. And they stopped at the Kyoto Observatory there, where they were hosted by Issei Yamamoto, who's the guy on the right, and his wife, at least I think that's his wife, who knew Wisconsin well. They had visited in the US some years before and spent some time at Yerkes Observatory, came to Madison for the 1927 AAS meeting, and then also spent some time at Harvard and I think out on the West Coast as well. So they knew the US well, and they knew Comstock from their time in Wisconsin. So the Comstocks visited them in Kyoto. Comstock retired to Beloit, and as Stebbins says, when he closed the observatory door behind him, he left the astronomy there. He was, that's not quite true because he was president of the American Astronomical Society, but nevertheless, Stebbins always says that the research ended and he played golf. Well, so Stebbins's summary on his old teacher, Comstock, was to try to put in perspective that Comstock was an old school astronomer, as he says here, in point of years, but his outlook was always forward. He saw the astronomy of his youth grow into the astrophysics of the present. Well, he not only saw it, he provided a lot of the fundamental data that produced it, ultimately, things like double star studies, masses of stars, proper motions of stars. But Comstock was also one of the generation of scientists who was deeply influenced, as we all still are, by Darwin's theory of evolution that came along in the middle of the 19th century. I guess I won't read the passage I was going to read because I've kept you too long already, but at the end of Comstock's introductory textbook on astronomy, one of several that he textbooks that he wrote, he concludes by talking about how the one thing, there's so much that we can't be sure of. We can study the universe now, but we have just the dimmest insights into how it got this way or where it's going. But the one thing the one great fact which stands out clear in this connection is that of change. The old concept of a universe created in finished form and destined to abide, the old concept of a universe created in finished form and destined so to abide until its final dissolution has passed away from scientific thought and is replaced by the idea of slow development, a universe which is ever becoming something else and is never finished. So I'll give Comstock the last word there. Thank you for your attention. Sorry about running over.